This video is about how to write a periodic function into its Fourier series. In the previous video, I talked about a brief introduction of Fourier series and the basic idea of Fourier series. So, to write a periodic function into Fourier series, we are talking about two different cases. The first one is we talk about how to write a periodic function with fundamental period 2 pi into Fourier series. So if you want to know more about the fundamentals period, I already mentioned in the previous lecture, so you can check my previous video about the definition of fundamental period. Now after doing that, we'll talk about how do we write a periodic function with a general period into its Fourier series. Okay, in this video, I'm going to only focus on step 1, which means I'm going to focus on how to write a function of t with fundamental period 2 pi into its Fourier series. So here we assume that a function of t has a fundamental period of 2 pi. So its Fourier series is given by this form. So this is a Fourier series, which is ft can be approximated by a function, which is a periodic series, is given by a0 plus summation of n from 1 to infinity an cosine nt plus bn sine nt. So I want to emphasize here, so first one you do have a0, but I don't have b0. There's no b0 over here. And I also have a1 until n infinity. So this is an, when n starts from 1 to infinity, an times cosine nt and bn times sine nt. So we have a0, a1 until a infinity. Basically, we have b1, b2, so on and so on until b infinity. We don't have a0, so there's no b0 here. So this form is called a Fourier series. And also, as I mentioned, as I emphasized before, we don't have a b0 over here. So all those parameters, a0, a1 until a infinity, b1, b2 until b infinity, they are called Fourier coefficients. Okay, so those are actually those ones we want to determine because this form are already given. So those are unknown. For given function ft, our goal is trying to figure out what is the a0, a1 until a infinity, what is the b1, b2 until b infinity. So that's our main goal, to find the Fourier series of a function ft. So the key, like I mentioned before, the key problem is how do I find those coefficients? Okay, so as a matter of fact, this coefficient is not there's an analytical forms for finding those coefficients. In particular, this a0 is 1 over 2 pi integrating from negative pi to pi ft over dt. So again, I want to emphasize over here, so this one, the fundamental period, here we're talking about ft has a fundamental of 2 pi. Okay, for general fundamental period, we'll talk about it later on in the next video. So this is where we talk about how we compute a0. It is nothing but the integration of the original function from negative pi to pi and then divide by 1 over 2 pi. Okay, divide by 2 pi, sorry. That's it, a0. So an for n from 1 to infinity, which means for a1, a2 until a infinity. Okay, so each ai is computed by an is computed by 1 over pi. Integration from negative pi to pi from ft times cosine nt over dt. Okay, and let me compute this one. So bn is 1 over pi integrating from negative pi to pi ft times sine nt dt. So if you remember if you want to remember this one, so a0, the difference is integrating is 1 over divide by 2t. Okay, 2 pi. Sorry. An for bn is 1 over pi. So there's there's no 2 over here. It's 1 over pi, 1 over pi. The integration is the same. So it's always integrating from negative pi to pi. For a0 is cosine is ft. For an, for n from 1 to 2 to infinity, so you time cosine t. If you look at this one, the original is a Fourier series. So it's relatively easy to remember because Fourier series is an times cosine nt. So when you compute the an, you also do ft times cosine nt. So if this is cosine, no, this is cosine. Okay. Similarly, bn is integration of ft times sine nt over t from negative pi to pi, then divide by pi, of course. So this is a sine because the bn in the Fourier series is bn times sine nt. So this is the same. So this, if you have cosine nt, you have cosine nt for that one to compute that coefficient. If you have sine nt, then you just, when you compute that coefficient, you also include sine nt. So that's how you remember this. Okay. So this is how we find the coefficients. The next question is why those one are a0 is given by this, an by this, bn by this. Want to know why? Okay, so actually this is pretty straightforward to figure out why that's the case. So if we assume that's the case, we want to figure out what's the a0, right? Let's assume that's the case is true, right? According, if this is the case, which means ft is given by this. If that's the case, if we do integration on both sides, okay, integrate that by integrate over t from negative pi to pi. So the left hand side is just ft, integrate ft from over t from negative pi to pi. The right hand side, I just copy everything from here, integration of over t from negative pi to pi. That's the same thing, right? So when then we can split, right? Because a0 is a constant, so it's integration from negative pi to pi, a0 over dt. This is a number of, we can move the summation outside because summation and integration they can swap. We can move the integration out as a summation outside. Inside will be integration from negative pi to pi, an cosine nt plus bn sine nt over dt over t. So let's do the integration. The integration says integration of negative pi 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 of a0 over t will be just a0 times t and evaluate at negative pi and pi. This one is a summation. We still keep the summation. The inside integration is quite straightforward. So the an times cosine nt, the integration will be an divided by n times sine nt, and bn sine nt, the integration will be negative bn over n times cosine nt. Okay, value at negative pi over pi. So here we have a0 of this guy, just evaluate a0 times pi minus a0 times minus pi, so it's a0 times 2 pi. This guy is 0 because sine pi is 0, cosine pi is 0. And sine pi, cosine n pi, and cosine n pi, they're all negative 1, so they all cancel out. So this will become 0. Essentially cancel out. So this one just become a0 times 2 pi. Okay, then we can say, hey, a0 is just given. If you divide both sides by 2 pi, we get an a0 is just 1 over 2 pi times this integration, right? That's why we figured a0. So how about a1, an? For an, you do the same. We do the same thing. The only difference is we do integration of both sides, okay, both sides of this relationship by cosine times both by cosine k pi. Okay, k can start from 1 until infinity, basically. Okay, if you do the integration of both sides times n cosine k pi kt, so this has to be t. Sorry, kt. Okay, you over from negative over integration ft times cosine kt over t from negative pi to pi on both sides. Of course, on this side you do, this is repeated, this is ft. At time cosine kt, that's the same thing. And over dt, that should be equal, right? If the previous Fourier series holds, so that should be true. So let's do the computation of right hand side. Right hand side would be integration from, we do split that as two terms. Integrate from negative pi to pi, a0 times cosine k pi dt plus summation of it, also move the summation outside. The integral inside, I divide into two parts, okay? Okay, first I do divide, so I time this one inside, so it becomes integration from negative pi to pi, an cosine nt times cosine kt plus bn sine nt cosine kt, so that's what we have. So this one, if you do the integration, an cosine kt will be just a0 divided by k sine kt, and negative, evaluate negative pi to pi. This is 0 because sine k pi is 0, cosine sine negative k pi is also 0, so that's gone. And then we can split this one into two terms. This is a product is a little bit hard to do, so we use the trigonometric relationship for the sine cosine product, so we can get cosine times cosine is half, cosine alpha plus beta plus cosine alpha minus beta, which means cosine nt minus kt. I merge them together, the cosine n plus kt plus cosine nt minus kt, which is cosine n minus k times t, divided by 2, of course. We keep it over here. Then the sine times cosine is, according to the relation given to the left, is sine alpha plus is sine nt plus kt, which is sine n plus kt plus sine n minus kt. Okay, we do the same thing, right? We do the same stuff. The reason this one, if you follow the previous one, because sine is always 0, right? It's always 0. Okay, so it doesn't matter. So it doesn't matter whatever you have. So this is be gone from the previous calculation over here. So it's still gone, right? So we only left with this summation from k to 1 to infinity, integration of negative pi to pi an times cosine. I split this 2 as cosine n plus kt divided by 2 kt divided by 2 dt, and integration from negative pi to pi an times cosine n minus kt divided by 2 over dt. Okay, so if we continue doing this one, because cosine nkt is also right over here, cosine nkt, this is always also 0, so it doesn't matter. This is always, because this has to n minus n plus k is always positive, of course, so this will be 0 again. So for this guy, this one also so we only left with this summation from k from 1 to infinity, integration from negative pi to pi an times cosine n minus kt divided by 2 over dt. So this guy we can rewrite as when k is equal to n is k not equal to n. When k is not equal to n is summation from k to infinity. When k is not equal to n, this guy again integration is also 0. It's also 0 according to what we mentioned over here. So it's 0 for any n, which means as long as n minus k is not equal to 0, so this is also 0. We only left with integrating from negative pi to pi an times cosine 0 times t. Cosine 0 t is just 1, okay, because cosine 0 is 1. So it's just 1/2 n over dt. So integration of 1/2 an over dt, half an by dt is just 1/2 an times t, evaluate negative pi over pi. So this integration is just an times pi. The right hand side is just an times pi. So if we divide both sides by pi, we can get an is 1 over pi integration of negative pi and pi ft cosine nt, because k is equal to n. Okay, so an by this. Okay, we can also similarly doing this to compute this. Bn is 1 over pi integration from negative pi ft sine nt. So what we do is we just do this negative pi ft times sine kt over here. So you do right hand side, you do also sine kt. You do all the stuff, all the follow the same steps. You can compute Bn given by this. Okay. All right. So by looking at this one, we also have some very nice product we can say. Okay, by looking at this product, because I compute the product somehow over here, and over here. You see, this is always 0. It doesn't matter what you're using right over here. So they are very nice property we can observe of the integration of negative pi cosine nt sine mt. For example, this is a property called orthogonality property. This is called orthogonality property. What orthogonality means, the integration of negative pi cosine nt sine mt will be equal to 0. Doesn't matter what n and m, as long as m and they are positive integer, is always 0. Okay, it's sort of the proportional, right? It's orthogonal, right? The product will be 0. It's sort of the product. It's like the dot product. Dot product, you get as orthogonal. They'll be 0. The product will be 0, right? And also we have the integration of negative pi to pi cosine nt and cosine mt. They are also orthogonal, meaning that the cosine nt times cosine mt integration from negative pi to pi will be 0 if n is not equal to m. So there's a condition which is not for all n and m. As long as n and m are not equal to 0, of course n and m should be positive integer. Similarly, integration of negative pi to pi sine nt and sine mt also equal to 0 over dt, of course, equal to 0 if n is not equal to m. Of course, it's n m is positive integer. So that's called orthogonality property. So orthogonality property is used a lot in the computation of the coefficients of the Fourier series because this can simplify a lot of computation. Okay, so now we're going to go over one example to show you how we compute the coefficients. In other words, how do I find the Fourier series for a given function with a fundamental period 2 pi? So here, let's say, assume that ft is a periodic function, a rectangular function with 2 pi as the fundamental period. In particular, ft is given by -1 if t is within 2k pi minus pi, and from 2k pi minus pi to 2k pi will be -1, and then the ft will be positive 1 if t is within 2k pi to 2k pi plus pi. So what this means, I'm going to draw the picture out. So if I draw the picture of ft is sort of given by this. So it will be positive 1 from 0 to pi, and -1 to pi to 2 pi, and the positive 1 to 2 pi to 3 pi, you keep the same pattern. So this is what ft looks like. So this ft has a fundamental period of 2 pi because this is a period. So after that, it will repeat again. Okay, so the fundamental period is 2 pi. Okay, so we want to compute the Fourier series of this ft. Okay, in other words, we already know the fundamental period is 2 pi, so its Fourier series is given by this. This is the form of my Fourier series. So we just have to figure out what is my a0, an, and bn. So that's what I'm trying to figure out. Okay, according to what I mentioned over here, how to compute the a0. Okay, this is how we compute the a0, and this is how we compute the an from 1 to infinity. This is how I compute the bn, 1n from 1 to infinity. So let's use that property. Just use the calculation, okay, to calculate what is the a0, a1 until infinity, what is the b1, b2 until infinity. Okay, so let's first compute a0. a0 is just 1 divided by 2 pi integration of -pi to pi ft. Okay, if we do this one, it will be just 1 over 2 pi. We keep that one. So this integration, because this one we separate into two parts. From -pi to pi, there's two. From -pi to pi, there's actually two pieces. They're not continuous. So we have to do this one is integrate from -pi to 0 of -1. So that's what I defined over here. And also have defined here is 1. So integrate from 0 to pi 1 over dt. So that's essentially this -pi to pi of ft. Okay. So the integration of -1 over t is -t, and the value of 0 and -pi. Integration from 1 of 1 is t, the value of 0 to pi. So I keep the 1 over 2 pi. So this one is 0 minus positive pi. So it's -pi. This is pi minus 0 is pi. So the sum of these two will be 0. Okay, so the a0 will be just 0 if you do that one. Okay. Now let's take a look at what is an. An is 1 over pi, according to what I mentioned. An is 1 over pi integration of -pi ft times cosine, right? Cosine nt. If you don't remember this, the integration has to be cosine because this is also cosine. So this has to be cosine. So the 1 over pi, don't have 2. You don't include 2 here. 1 over pi integration of -pi to pi ft times cosine nt. So it's 1 over pi. Again, we have to split into two parts from -pi to 0. So ft here in this case defined -1 times cosine nt over dt plus the integration from 0 to pi. This is positive 1 for t within 0 and pi times cosine nt. So integration of this guy will be just of this guy is negative. Negative is -1 over n times cosine nt. Okay, integration of cosine nt 1 over n sine nt. Okay, evaluate -pi with 0 for the first one and 0 to pi for the second one. So if you do this one together, so this is sine nt, doesn't matter what n you have. When t is 0, sine 0 is 0, sine n pi is also 0, so this is gone. Sine n pi also 0, sine n 0 is also 0, so this is also gone, so it's also 0. So it's become 1 over pi 0 plus 0 is 0, so the an is also 0. So this n is, it doesn't matter what n you have, so this is always 0. Now let's take a look at what's the bn. Bn is 1 over pi integration from -pi to pi ft sine nt, so the difference is sine, so we don't have a cosine, sine nt. So we follow the same procedure I mentioned before, 1 over pi over here. So split into two parts. One is the integration from -pi to 0, -1 times sine n pi nt, plus integration 0 to pi 1 times sine nt. So if we do it here again, so 1 over pi is integration of negative sine nt, which is cosine negative 1 over n times cosine nt, evaluated at negative pi 0, minus, so sine nt, the integration will be 1 over n times cosine nt, evaluated at 0 to pi. So I move this, now I move this n outside, okay, or outside, so it's 1 over n pi, cosine nt, negative pi, evaluated at negative pi and 0, minus cosine nt, evaluated at 0 to pi. So if we do this one, so I keep the 1 over n pi the same, so this one will be just when t0 is 1 minus cosine n pi. So this guy is, when t is pi is inside is cosine n pi, when t0 is cosine n times 0, cosine 0 is negative 1, so this is this one. So when we write them together, it's 1 over n pi times 2 minus 2 cosine n pi. Because this may not be 0, okay? In particular, if n is odd, which means n is 1, 3, 5, 7. For example, cosine pi is, we know, the negative 1. Of course, cosine 3 pi, this is also cosine 3 pi, cosine 5 pi, whatever, will be negative 1. But cosine 0 is equal to cosine 2 pi. It's not 0 because I'm talking. So cosine 2 pi equal to cosine 4 pi. They are equal to 1. So when it's equal to 1, this is 2 minus 2 is 0. So when it's even, so which means n is 2 and 4 and so on and so forth. So this will be 0. When n is odd, it's just, this is 2 minus 2. So it's 2 plus 2, which means I have 4 divided by n. Don't forget about this n pi. It's 4 over n pi. So when it's n is odd, it's 4 over n pi. When n is even, is this bn is just 0. So if you put them together, we have ft for the previous one I mentioned it. Ft is a0 plus the whole thing stuff. If we replace, because a0 is 0, this guy is 0. The bn only occurs non-zero when n is odd. So it's just summation from n from 1 to infinity when n is odd. When it's odd, this bn is 4 over n pi times sine n, here it should be t. Okay, so times sine nt. So that's the Fourier series for ft, the previous one, the example, which means I have summation. So for this function, is Fourier series given by summation n from 1 to infinity. N is odd, 4 over n pi sine nt. So that's the Fourier series for this function. So it's not very complex, and it turns out it's not very complex. Okay.